Physics in the Flesh. Welcome back to another simple harmonic motion problem. Number 4. A block of mass m is supported by two identical parallel vertical springs, each with spring stiffness constant k. What will be the frequency of vibration? So in this problem, we've got things given in terms of the variables. Okay, so k for spring constant, m for mass. So we're not going to be extracting a numerical answer, but rather an expression. And the expression for frequency will involve a constant, k's, and m's. So if it was 1k, we know how to handle that, right? We know that we can draw the free body diagram. You've got gravity going down, force of the spring going up, and that's it. But now we're trying to figure out, well, what happens if you have two springs? I mean, does the effective spring constant double? Does it get squared? Is it exponentially more? What happens? And that's what we're trying to figure out here. So we're going to start off by drawing a free body diagram of the situation when it's at equilibrium. Okay, so at equilibrium means it's in this state right now. So it's just hanging due to its weight. The springs have extended by a certain amount. Okay, so in this scenario, you've got the spring force of the left spring going up. We'll call it Fs1. The spring force from the right spring going up, Fs2. Bear in mind they're identical springs. And you've got the weight going down, Fg. Okay, now, because it's at equilibrium, we can say that the net force is equal to 0. So F net, and we're dealing with the net force in the y direction, is 0. Okay, now let's set a positive direction for this problem. Let's let up be positive. Okay, which means 0 is then equal to Fs1 plus Fs2 minus Fg. Okay, so let's replace Fg with mg. Fs1 plus Fs2 minus mg. So now let's make another expression. Let's bring the mg to the left, or rather have mg on one side, Fs1 plus Fs2 on the other. Okay, so Fs1 plus Fs2 therefore is equal to mg. So how does that help us? Well, this is at equilibrium, right? So we've made an expression of the spring when it's at equilibrium. We're asked in this question, what is going to be the frequency of vibration? Well, the spring isn't actually going to vibrate unless you move it, right? So you have to take that spring, extend it down, let go, and let it just go back and forth. So you have to displace the mass by x, all right? So this is going to be the second scenario we're going to deal with. This is going to be when we displace the mass by a distance x. Okay, downwards. All right, so let's draw a new free body diagram. If you now displace the mass downwards, okay, the spring force now is going to be a little bit more than it was before. Okay, so we'll call it now Fs1 prime and Fs2 prime. And of course, the weight doesn't change. Fg is Fg. All right, so let's do this, this system again. We know that in this case, F net y is equal to Fs1 prime, Fs2 prime minus Fg. So Fs1 prime plus Fs2 prime minus Fg. Now, here's the question. Well, what's Fs1 prime, Fs2 prime? It seems like, oh, sorry, guys. It seems like we're just making more variables for ourselves here, right? Let's try to express this in terms of Fs1 and Fs2. Fs1 prime, you had already a force Fs1 up here. So then all you did to increase it to this one is extend the mass downwards a little by distance x. And by doing that, you increase the elastic force. And we know that the elastic force is given by minus kx. The reason it's minus is because of the x. Okay, so when x is being stretched, it's a negative. When x is being compressed, it's positive. And that takes care of the negative sign there. So yeah, Fs is equal to negative kx. So if we extend the spring down by x, that means we've added an additional force minus kx. In other words, what I'm trying to say here is this. Fs1 prime is just the original force Fs1 minus kx. And okay, don't look at the minus as I'm taking it away. We know the force is getting bigger. The minus is from here, okay? We're adding the additional spring force. And because we're stretching, X is going to come out negative, all right? And by the negative X, this will become a plus. So this number is going to get bigger. So don't look at it like that it's negative, it's getting smaller. No, it's going to get bigger. Fs2 prime, therefore, is the same. Fs2 minus Kx, right? It's the additional amount it's extended by. So we're going to go take these and plug them into this expression right here. Okay, so Fs1 prime, Fs1 minus Kx plus Fs2 prime, which is Fs2 minus Kx, and then minus Fg, which is just Mg. Okay, so we've got a negative Kx here, negative Kx here. I'm going to bring that out to the front, call it negative 2Kx. And then I've got plus Fs1 plus Fs2 minus Mg. Well, hopefully you see what I'm about to do here. Check this part out. Fs1 plus Fs2 minus Mg. That's exactly what we have here, right? Well, except we have Fs1 plus Fs2 equals Mg. Or rather, you can even call this equation is actually a bit more helpful here. 0 equals Fs1 plus Fs2 minus Mg, right? So this is 0. That's equal to 0. So this whole thing disappears. And this is due to 1 star. Okay? So if that disappears, that tells us that the net force in the y direction is equal to negative 2Kx. Now, how does that help? Okay, what is the net force in the y direction helping us with in this case? Well, the net force, the additional force that we exerted to go from here to here, is that additional spring force, right? So if you want to take this, you compare it to the spring force. Fs is equal to minus Kx. Now, what similarities and what differences do they have? Okay, so in this case, we're assuming the net force to be the spring force. X is the displacement in both cases. So how did the value of K differ? Well, K doubled. K became 2K. Okay, so K doubled when you added an additional spring. So it didn't become K squared. It didn't become like an exponential. So here, let's just go ahead and find the frequency of vibration. Now the frequency is the standard formula we've been using back in videos 133 and 132. So the frequency of vibration F is given by the formula F is equal to 1 over 2 pi square root K over M. Now I'm going to write K effective only because it's not one spring we're dealing with here. It's the effective total spring constant of the two springs together, which is 2K, right? We just found that. So 1 over 2 pi square root 2K over M. And that is your frequency of vibration. So that's it for this video, guys. I hope you enjoyed it. If you did, be sure to smash that like button and subscribe to Physics in the Flesh so you never miss a video from me. Also, guys, in case you didn't realize, the frequency went up by root 2, right? Because the 2 is under the square root compared to this expression. The frequency didn't double, although the spring constant did. Frequency went up by square root of 2, a factor of root 2. Anyways, guys, I'll end the video there. Enjoy the rest of your day. What? Wait, who's back to school? Pumpkin pie recipe. Okay, I'll save that for Halloween. Guys, so that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button and subscribe to Physics in the Flesh so you never miss a video from me, which, by the way, I post every weekday at 12 noon. So be sure to be on my channel at that time. Guys, as always, if you missed my videos from the past, be sure to click over there on the right. You'll see some of my latest videos there. And other than that, guys, I hope you enjoy the rest of your day. Peace.